Hello everyone, let's start the lecture for today. Today we start the Aitken acceleration and later on we'll discuss the second method and that will be the end of this chapter. So for in this method, the Aitken acceleration, we'll learn how to accelerate the convergence rate for a linear convergent function. So that means this method is for a function for which lambda is constant but non-zero constant. And note that lambda is defined as the ratio of the error terms in the limit k goes to infinity. So whenever lambda is constant but less than 1 greater than 0, then we call it linear convergence. So now so what we do that if we know lambda for some convergent function, then we can solve for the root or x star in terms of lambda, which is given by this equation here. X star equal to xk plus 1 minus lambda xk divided by 1 minus lambda. Okay, so now so but if lambda is unknown, then it can be eliminated from the above equation by equating nearest pair of iteration points. What I mean here is the following: in this equation here there are pair of points. If we take two pair, then we can put them equal because lambda is constant, so then we can eliminate lambda and solve for our equation. Okay, so that is the idea. So we take three nearest iteration point xk, xk plus 1 and xk plus 2, and we compute lambda using two pairs, nearest pairs k plus 1 and k plus 1 k plus 2 to eliminate lambda. So that is our equation here. So you can see that is lambda equal to this one and also this one. Okay, and now what we do some algebra here, and then see what is going on. Solving for x star gives us this equation. So we now do some algebra to solve this one, and we can write in this format x star equal to ratio of two terms. Now these two terms can be written in a simplified form. The x star equal to xk is kth iteration minus the other terms, which is xk plus 1 minus x whole square divided by xk plus 2 minus twice xk plus 1 plus xk. So therefore the iteration formula is given by this one, xk plus 2 hat equal to xk minus xk plus 1 minus xk whole square divided by xk plus 2 minus twice xk plus 1 plus xk. So hat is a symbol, we use a new symbol, and this value xk plus 2, to compute that one we need 3 points, k plus 1 and k plus 2. Look at that is your xk, that is xk plus 1 and xk plus 2. We need this 3 point and then find the new point xk plus 2 hat. So this is the value, we call it accelerated value, because this, as you're going to see, the value coming from that hatted quantity gives you less error than the unhatted quantity here. Now using the forward difference notation, we can express the above formula in a very simple form. That is just pure notational fact. The change in xk is by definition that is the difference. So using this notation, we can write the numerator in that format, and the denominator we just rearrange this format. You can see it is the notation. Sometimes we use the delta notation in many textbooks or also in some lectures. You can find it very quite often. So in this delta notation, we can write the iteration formula as xk plus 2 hat equal to xk minus delta xk whole square divided by delta e square of xk. That is a simplified notation, but actually that is the equation that we are going to use here. So now, starting from x0, every two iteration after that means the every third iteration point we have a accelerated value. So accelerated means that the iterated point becomes more close to the root or x star. That's a diagrammatically like that. We start from x0, then compute x1 by iteration formula, and then from x1 we compute x2, and then we apply the Atkin acceleration formula that we saw in the previous slide, and then we compute x2 hat. So now this x2 hat we treat like an x2. So remember that this x2 here is not this x2, so not the same. Okay, so we are treating that these two are same. Okay, so now what we do, we take this x2 hat as a new x2 and then apply iteration, compute x2, and then from x3 we compute x4, and then apply the acceleration again, we compute x hat 4. So then from x4 hat we take this to be as new x4 and then apply iteration again, so x4 to x5 and x5 to x6 hat, or x is actually not hat, it will be x6, and then from here we compute the x hat. So our iteration applied in here and here and also here. Okay, that's how it continues until we get our error within the bound. So let's, for example, here to further clarify, consider the sequence x2 to x2 hat to x2. That means here x2 to x2 hat up again x2. What does it mean is the following. Here the first x2, meaning this x2, has been accelerated to get x2 hat. This new value of x2 or hat has been treated like x2. That means these two are equal, same. And then we apply from here the third iteration to get our x3. That's how does it work. So now starting from x0, so we get x2 as after third iteration, and then from there next third iteration gives you x4, and the next third iteration gives you x6, and so on. So now, as for example, consider the function f of x equal to 1 over x minus 0.5. Clearly, for this function, we have f2 equal to 0. So we have the root, which is 2. Let's now construct g of x to find the fixed point of g of x, such that f of x will be 0. We consider g of x equal to x plus 1 over 16 f of x. So if we put the f of x here, that is a simplified expression, and you can easily check that if you put x equal to 2, it is really equal to 2. So that you can see by explicit computation. So 2 is the fixed point of g of x or root of f of x. Now check the convergence. So compute the lambda, which is by definition g prime at x star. So we compute the derivative of this part here, and then put x equal to 2, and we get it is 0.98475, which is just it's less than 1 but very close to 1. Since it is very close to 1, it means that our convergence will be very slow. Remember, lambda equal to 0 is super convergent, lambda equal to 1 is the upper bound. So lambda has to be in between for linear convergence. Since it's close to 1, so we are expecting very low convergence. So let's start the iteration with x0 equal to 1.5, which is close to the root 2. Okay, and now up to 7 significant figure we compute. Your second significant figure means that we have to match 7 digit, and error will be in the 8th digit. In other words, if you subtract and compute the error will be within 10 to the power minus 6. That's what it means. So now let's do the calculation. We start from x0 equal to 1.5 here, and then compute x1, that is your g of x. By definition, g of x0 is x1, and that is your error. And then compute x2, so you can very easily follow the iteration process. It is very familiar to all of you. So x1, x2, x3, x4, we continue computation, and you can see the errors are decreasing but very slowly. Okay. So, and we want this error to be here within 10 to the minus 6. And you can see here that after 818 iteration, we get our desired error, which is less than 10 to the power minus 6. It's a huge number of iteration. Okay. So, and the Atkin acceleration tells us that how to make it faster convergence. So what do we do? Let's do the calculation again with including Atkin acceleration. We start from x0 equal to 1.5 and then compute x1, which is same as in the previous slide, x2 exactly same as previous slide. Now we compute x2 hat. Okay, so x2 hat is that Atkin formula, and you can see x2 hat is 1.877604. The error is 0.1222396, which was 0.4 something for the x2. Okay, so it is very much reduced. Now in the next iteration, we use this value of x2 here and compute x3. That means x3 will be g of x2 hat. That is our new x2. And we compute x3 and x4. Now we iterate we accelerate x4, which is x4 hat. We get new value, which is 0.007366. We continue this way, and you can see after each iteration, we get a desired result. So it is very fast convergence. Okay, that is the effect or implication of Atkin acceleration. So by using this method or technique, we can accelerate the convergence rate for any linearly convergent iteration. Now next, there is a second method. So this method actually is the modification of the Newton's method that we did one or two classes before. So recall that in Newton's method, our iteration formula was xk plus 1 equal to xk minus ratio of f of xk divided by f prime of xk. Okay, and the above formula, this formula required that at each iteration point, we need to calculate the first derivative and check if it is 0. That is a drawback. Moreover, if f prime of xk is very small, then loss of significance may occur, which is a very problematic fact. Okay, so what do we do here? To avoid this drawback, we replace f prime of xk, means first derivative, by an easily computable function. We call it g sub k, which is approximately equal to the first derivative of f. This technique is known as the quasi-Newton method. Okay. In particular, if we choose gk to be the backward difference between the nearest iteration point, then we call it a secant method. And this method is also introduced by Newton himself. There are other methods like the Stephenson method or any others we will not discuss here. We are just going to discuss the second method as an example of quasi-Newton method. Let's see what it is. The backward difference formula for the nearest iteration points is the following: g of sub k equal to, that is the rise difference, and that is the run, the denominator. You can see that it is actually a slope formula between the nearest iteration point. Okay, so we use this value instead of the f prime, the first derivative. So if we put it there, then we can rewrite our iteration formula then in this format, and that is known as the second method. Okay, so now what do we do here? To apply this iteration method, you can see that to start the iteration we need 2 points, not a single point, unlike any previous method. In any of the previous method, we start from x0 single point and then start the iteration, but here we need two initial value, x0 and x1, and then we compute the x2, but afterwards we just continue the iteration, because once we compute x2, then we can use x1 and x2 compute x3. and from x2 and x3 then you can compute x4. So that's how the iteration goes. So initially we need 2 iteration points to continue the iteration in this method. And secondly, the advantage of this method is the following: only one function to be evaluated per iteration. For each iteration we just need to compute f of xk for that particular, not the derivative. So we have a very simpler case here. Now take an example: f of x equal to 1 over x minus 0.5. That is same example, and let's choose x naught initial point 0.25 and x1 equal to 0.5. Okay, and you can see here very easily that our first iteration point is not x1 but x2. Remember, we start with two initial points, x0 and x1. Now we compute x2 by the second formula, and here is our x2, and that is the error. Now use x2 and x1 to compute x3. That is our error term. Now if you continue this way, you can see that after each term I get an error which is the 0.05134888. You can see it is very fast decreasing, but that is the case. So hence the convergence is very fast, and we need only 12 iteration to match the machine epsilon. You can see that it is very fast. Since the error is decreasing, this is super linear convergence. What we mean, that look at that is a lambda actually ratio. So you can see here it is decreasing 0.75, 0.75, 0.65, 0.49, 0.32 and so on. It's decreasing. So it is going to 0. So in the limiting sense, as k goes to very large or infinity, that ratio goes to 0. That is the property of a super linear convergence. So actually this second method is a super linear convergence method. Now let's see graphically how does it look like. Okay, so if we draw this graph here, suppose that is our f of x. Okay, so this point is our x star. So we choose x0 here and x1 here, and we draw a slope formula. We draw a line here. So it intersects the axis at this point here. That is our called x2, and then go back here. That is our new point on the curve, and then we choose other point. That is how does it work. Okay, and so finally we study the theorem, and in this chapter the theorem 4.6 states that the order of convergence is 1.2 over 5 by 2, which is 1.618. Remember, this is in algebraic notation, this is called the order of convergence alpha, that we discussed long few lectures back. So if f star of f prime of x star is not equal to 0, and for x0 and x1 are very close to the x star, then this method is a very well defined method and it gives the convergence very fast. That's all about the second method, and we stop here, and this is the end of this chapter. Thank you very much.